Okay, good morning, everybody. How's the project going? I know she's got all the right answers. I checked her answers last night or this morning. When did I check them? Last night. So check with her if you want to know if you got them right. Everybody know who she is? She's Fatina. And she'd be very happy to tell you all the right answers. Okay, so keep working it. So we're going to move from Bayes to Fischer's linear discriminants today. Slightly different topic, but everything kind of builds on it. So it's new, but it's not new. And this is based on some really old math. Now you got to think back, what were things like? They didn't have computers back then. They didn't even have handheld calculators back then. So they needed to do things out much more theoretical. And so he's kind of looking and saying, well, what can we do and how can we rearrange our data in a different way of looking at it? Okay, so he was saying, okay, what can we do? And he had a really good grasp of the mathematics because they studied a lot of theoretical math. They didn't have to spend all their time taking computer science classes and all these other stuff because they hadn't been invented yet. So he had the math. And this math appears lots of different places. And everybody keeps rediscovering the wheel. So the same exact math is what shows up in something called the Hotelling transform. And I'll just show an example of that in a little while, just to give you another visual for another way of thinking about the math. Eigenvectors, okay, it's that linear algebra that you guys have taken and you totally mastered and you totally remember. If you calculate eigenvalues and eigenvectors, which you need to do for this, is an eigenvector transform, which is just done in linear algebra classes. For any of the grad students who've taken 660 here, linear systems, equivalent to that, this offered at every university. You'll use that there. Principal components is an extension of Fischer, which is used a lot in pattern recognition as well. And we'll talk about that later on. Principal factor, the Cahunin-Loew transform. I don't expect you to know what they all are, but I want you to hear these words. Because when you come across these words in other contexts, I want you to reach back to this knowledge and pull it there. So when you go off and you take a course that uses the Cahunin-Loew transform, and you say, the what? You can say, I've heard it before. And I remember everything from my pattern recognition class. And so I'm going to be able to use that information there. It's used with a pre-whitening filter. If you've got a couple of different objects, a signal and a noise, you can remove some of the noise mathematically. It's different than filtering, but it's a way of different mathematically looking at it, where you're able to remove some of the noise. It's used in regular filtering, used in factor analysis. Again, the same math shows up in lots and lots of different places. And I just want you to see how powerful it is. And it's all based on something that somebody did almost a century ago. And it's still used and it's still useful. So from an advanced image processing class I sometimes teach, here's some examples, or things might be a little bit out of order here. So what Fischer was talking about is if we have data, those X's and O's, and we have feature 1, feature 2, so we can have feature 1 and feature 2. And we can say that our points are built out of feature 1 and feature 2. And if we try and classify with them, we can do that. But we can do a better job of separating them because here they've only got that much space between them. If we rotate and look at things on the side and we project all of our points down to this other dimension, we can then have a bigger gap between them, and we can divide there. And we've got to now have a bigger space. Now in here, we could divide with the original coordinates, but if I were to move one of these x's and put an x, let's see where I can, how do I arrange that? There we go. If I put an x there and I put an O there. Now, I cannot draw a line this way and separate them. But if I go this way, I can separate them. By changing how we look, we can now make them separated. And so the idea is that we can go from any dimension, we can reduce our dimension, and reducing the dimension then means you also have less data you need to work with. And you can still sometimes classify in these other directions with fewer features. So we're projecting it on a line, W transpose X. Every point's going to be transposed, every point's going to be projected onto the line W. And because W is a 2 by 1 and X is a 2 by 1, Y is a scalar. We've reduced our dimension, and we can quite often increase separability. If we find the right W. It would not work if I made a W, oops, that's not a straight line. It would not work with that W. That would then mean we're projecting everything here and everything's getting jumbled together. That would be a bad one. And then there's some other ones which are medium. This one here might work, but it might not be as best. So the question is, we want to project, but what's the best line to project it onto? There's some good choices, there's some bad choices, and there's some medium choices. We want to optimize and find the best choice that will project and separate things the best. So here's some other examples. If I project it onto that W, they're still separable. If I project onto that one, they are not separable. And this one here in the top right is the most separable. There are good choices, there are bad choices, there are medium choices. And the goal is to find the best projection. So how do we define best? What makes the one in the top right better than the other two? Remington? The distance between the two nearest X and O is one possible way of describing it. What else? Yes? So he's looking at the individual X's and O's as clumps and individuals. Yes? Say, the spread of each set is minimized. And what else? We want the means of those to be further apart. So Remington was talking the individual, you're talking about the pieces. And if we look at them, so we want the spreads minimized. So we have very compact clusters. And we want the means of those clusters to be further apart. Because if they're further apart, we can separate them. Not everything is fully separable. This case here, the two things are linearly separable. But sometimes they do overlap, like you saw in some of with the GUI on the two-dimensional Bayesian detection. You can still you're trying to minimize your error. So here we're still trying to minimize the error. Here's a case where we can do linear separability with 0 error. But the same technique applies when there is error, when they're not linearly separable. But there, the best would be separate those means, and let's do the best we can. I think everybody agrees that this lower left is not a good choice. So we want the means to be far apart. But what does far apart mean? Look at these two examples I've drawn on the bottom. Those means for both cases are the same distance apart. But what's different between the top and the bottom? The standard deviation. So just getting the means apart by the same amount doesn't help. We have to at the same time reduce that spread, make them more tightly packed. So we want a large distance between the means. We want small standard deviations for each individual. And we can take those two individual small standard deviations and write that as the sum of the standard deviations being small. And we know sigma is going to be positive. So we don't have any negative problems. And then we want to ask what vector W will allow us to achieve this. Is the question clear? What we're trying to do, and we're starting to get into the math, but you can see that math where it's taking us. So therefore, we define a thing called a cost function. And if any of you ever have the opportunity to take a course called optimization methods, it's usually offered in a lot of bigger engineering programs. I've found it one of the most fascinating courses I ever took. It's really a great course for electrical engineers to take. We don't offer it here very frequently. Got a couple of professors who'd love to teach it, but nobody would like to take it. But I do encourage you, if you see one offered, I do recommend it to you. It is very, very good for you. And an optimization methods course is built all around having a cost function. We always use J for the cost function. And then saying what things can we do to optimize that? Well, while you may not have taken an optimization class, all of you have taken a calculus 1 class. And all of you passed that calculus. So if I give you some arbitrary function and I'm asking you to find the minimum, how did you do it in calculus 1? Take a derivative, set it to 0, and that will find you all the different local minima and maxima. And if we have a function which is convex, which means from any 2 points, you can draw a line and you don't cross the line itself. Here, any 2 points, we cross the line, so that's not convex. If we have a convex function, then when we take the derivative and set it equal to 0, we're guaranteed it's either a maximum or a minimum. So in a lot of stuff we do, we say it has to be convex, and the good news is a lot of things are convex. Particularly parabolas. squared things. See some squared things? So we get a lot of convexity. And we're going to take a derivative, set it equal to 0. Okay, some math. Just so you know it exists. We have a projection. Projection is a dot product, the line in our vector. We can get the mean of our points prior to projection or after projection. So you're going to add up all your points and divide by n. No surprises there.
Excuse me, what's the notation about the MI?
It's our sample mean versus a theoretical mean. Okay. The tilde.
With the tilde is sample?
Yeah.
Okay.
So our sample mean is this. We can then substitute that in, add up over our points, and we can rearrange things. And what this is basically saying, where is it? Come on. Is that you can either project the points and calculate a mean, or you can take the means and project the means and calculate the mean. Doesn't matter which order you do it. Calculate the means originally and project your value, or project the points and calculate a mean. We want our sample means after projection to be far apart. That's what we said here. We want the means to be large after projection. After projection, we want the means to be large. So we want this distance to be large. So we're going to put in two different means. That's taking the magnitude squared, just as you multiply them by their transpose. We can then factor out omega transpose, factor out the omega transpose, which is an omega not transposed or W not transposed. And we're left with the difference of the means original means and the other original means transposed. Just a little bit of math. But this M1 and M2 without the tilde are the means of the original points in the original higher dimensional space for the pictures too. And so if we want the sample means after projection to be far apart, then we want this to be large too. W transpose SBW, W transpose difference of means, W. We want those things to be large too. If we want this to be large, we want each of these other things to be large. And we can take this stuff in the middle, the product of the means, product of the difference of the means, and we're going to call it a name called SB, which is a scatter between, the difference between the two means. Just the name that's been given to it historically. You can call it Joe if you want. But historically, it's been called a scatter matrix between. Because its dimension is going to be 2 by 2 for the case we started with. And any guesses on your data set what it might be? With the data you've been using for your projects? How many features do you start with? 8. So if here, where we got 2 features, it gives us a 2 by 2. For your work, your mean vectors are 8 by 1, 8 by 1. So the outer product of 8 by 1 and 8 by 1 is 8 by 8. You'll have an SB for your data That's an 8 by 8. This guy here will have an SB that's 2 by 2 because it's starting off with 2 features. So in order to separate those means as much as we can calculate this, and this is our metric we're trying to maximize. And because we want these to be small, we're going to take the ratio and say we can maximize this cost function if the numerator is big and the denominator is small. The whole thing will become big. 1 divided by small is big. Sound vaguely familiar for something you heard someplace, ancient history? 1 divided by small is big. So we want this to be big. We want these to be small. So this ratio, we want it to be big. So here's how we deal with the numerator. Likewise for standard deviations. After projection, y minus the mean squared added up across all your data points and divided by n, but why did I leave divided by n out? We're trying to maximize this. It's always going to be divided by the same n. So it doesn't matter if we divide by n or don't divide by n, it's still going to be the same maximization. So we're going to leave the divided by n out, or divided by n minus 1 out, because it doesn't come into play when we're trying to maximize. So our standard deviation for our projected points, take your point, subtract the mean, square it, add, 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 add. You've done this before. I know you've done this before. We're just skipping the divided by n. Okay, that yi is a projection of our original points x. And that mean estimate is a projection of our non-projected means. That squared, we can take that squared and do it as a product. Lots of good vectors. Factor out that w, factor out the w. And we wind up with all these pieces in the middle. And this is taking our data point minus the mean, data minus the mean, transpose, outer product. That's the same thing you're doing for your project to get your covariance matrix. And so that is an outer product. That is a matrix as well, SI. And you're going to get one of them for every class. And in a 2-class case, we'd add up those 2. And we're going to call it SAM, or SW, the within scatter. Pick a name for it. The community calls it SW. You can call it whoever you want to call it. We got 2 classes. We want each of them to be very narrow. 2 classes want each of them to be very narrow. So rather than talking about them individually, we're going to combine them. We want them all to be narrow. So we've got a term that's related to our denominator. We've got a term that's related to our numerator of our cost function. So what's next to find your optimum? Back to Calc 1. What do you do next? Derivatives. So we're going to take our cost function. We're going to substitute in the different way of writing it. And we're going to try and maximize that. Okay. Now you can take derivatives and do whatever. But this Fischer guy did a lot of reading. And there wasn't nearly as much stuff published back then, so there wasn't nearly as much stuff to read, so he could keep up on his reading. And he realized that this mathematical form appears many times, and somebody else solved it already. And if somebody else already solved it, no reason to reinvent the wheel. Hey, I know how to answer that. This Raleigh guy who did some work in mathematical physics came up with the same thing. And he said, hey, I know how to solve that. So Raleigh published a paper, somebody else published it about Raleigh's work and said, hey, I know how to do this. And the answer is eigenvalues and eigenvectors. That's why linear algebra and the linear systems class are good for you. They show up all over the place. So in order to maximize this, you can go through a lot of math, but it's all going to work out to those derivatives, saying that you get this other form of the equation. If you can solve this other form, if you can solve this form of the equation, that will maximize this function. And because this is the matrix and this is the matrix, we can bring it over. The lambda is a scalar. And then we wind up with lambda being an eigenvalue and W being an eigenvector of this compound matrix. And going back to that Raleigh guy, you can solve it this way if C is 2, if you've got two classes. Take the inverse of your within matrix, take the difference of your means, and multiply them. We'll talk about the method if there's more than two classes later. First, I want to see if I can get everybody to sort of understand when there's two classes. So you can take this, you can find eigenvalues and eigenvectors. And if there are two classes, you can shortcut and say that your eigenvector is going to be this. Jacob.
So what was omega again?
W is your projection vector.
And how did we find that?
This is how you find it. You're trying to find a projection vector.
Didn't we use the projection vector to calculate the
We said of all the possible projection vectors, this is what the projected means and projected standard deviations would be. And now we want to optimize it to say what's the best choice. So it's not that we've found the means for one specific projection vector, but these formulas are what would it be for any projection vector. And then if we find the best one, it's going to maximize this. So it will be this for any of them. And if you pick a good one, this term will be big. If you pick a bad W, that term will be small. If you pick a good W, the difference in the means will be big. If you pick a bad W, the difference between the means will be small. Yeah, M's and mu's are same thing. And here it's talking about kind of a pure distribution versus a sample mean. What are the samples from a pure distribution? Whether you're measuring it or taking it as pulling from the theoretical distribution. So we can find the vector that's going to give us the maximum distance between the means at the same time as the smallest standard deviation for each individual class. And this is one way of calculating it. And with that, we know which W we want to use. When we know that W and we know our data points in our higher dimensional space, we can then use that W to project those points from the higher dimensional space down to a scalar space. We've reduced the dimensionality of the problem. We made it a little bit easier to solve with a lower dimensional space. So if you have a really, really high number, it can make things computationally more simple. Slow down, take those computers that are being slowed down because you got a lot of data by reducing the dimension of it. Also, analysis of this W can tell you which of those original features was most important. We look at this case, we've got feature 1 and feature 2. Which of those two features was more important for helping you separate those classes? X1. Now the pictures aren't drawn perfectly here, but that W was going to have more weighting on the X1. So it can tell you which of your features was more important. Here you can eyeball it. That 3-year-old in the box. Computers are terrible at looking at large clumps of data and just looking at it and saying, oh yeah, it has to go measure, 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 calculate, calculate, calculate in order to say this. But if we were to pick the W for this lower picture, that's a bad one. But the other direction says that it's the X1 which was more important. And so if you have a high dimensional space with a lot of different features, this technique and then looking at your W, that W, the coefficients, can tell you which of those features were more important. Because as it takes a projection, it takes more of this and less of that. So which one is it taking more of? Which one is it taking less of? And it can tell you which is more important. Remington, you had a question.
Yeah, so W is always the same amount of features that we have given.
W is always going to be the same dimension as your feature vector.
And then it sort of assigns like a number to each one.
Mhm.
See where one's the biggest and that one's the most.
And then looking at the magnitude of the elements in W, pair them up with your original feature vector, and it tells you which features, how they contributed, which ones were contributing more, which ones were contributing less in the projection. So this technique can separate things, bring your dimensions down, make your computers run faster. It can also provide you with information about your original data, if you can't just sit there and look at it. How good are you guys at looking into 8 dimensions? What about 100 dimensions? Yeah. So these are techniques that you can also use to tell you something about your data. So you pick some data, you got the data, you can then say, did I pick some good data? Well, you can try this combination or that combination, like the grad students are probably doing a little bit in the project. Or you can go and analyze it and have some expectation about what you think is going to work based on the analysis. Which features are likely to be more important based on the weighting of the optimal projection. And that can also then tell you, should I keep these features or toss them? If you're up at 100 dimensions worth of features, are all of them helpful? Probably not. Which ones are more helpful? Well, let me take this pair and try it. Let me try this pair and try it. If you've got 100 features, how many combinations do you have of 2 features? A lot. How many combinations of 3 features do you have? A lot. And is it better to have 2 or 3? And which 2 or 3? Or maybe it was 4 was the right answer. You should have had 4 features and not 3 features, but which 4 out of those 100? You get the idea that there's a lot of possibilities of which ones are good. So having a tool that can help you figure out how to look at it a little bit quicker can help you some. Remington.
So if you're trying to like select the features to enter something, if you want to select features that have a similar W weights to them.
You want features that have large W weights, ones which are more important. In this example, because they were already separable, you can get away with just taking x1 and tossing x2. Right? You could get rid of the x2. We can then just divide just based totally on x1 and we're good. If 2 dimensions was too much for you to handle, you could just toss x2 and you could still live with your results with just x1. Now, having a little bit of x2 in there is good, because it gives you a little bit more space, because you don't know what points you haven't seen yet. So you don't know what other points are going to be floating around that you haven't seen yet. So you might want to have a little bit of extra buffer. But if 2 dimensions was too much for you, and you just couldn't do it with 2 dimensions, he just didn't have enough calculation power, and he needed to get down to just 1 dimension, he would jettison that x2. Or he could take a linear combination and get a little bit of x2 helping boost things. 2 dimensions down to 1 is not a real big deal, but 100 dimensions down to 20 is a big help. Having some idea, well, how do we take those 100 down to 20? How many possibilities of 20 out of 100 are there? A lot. So you don't want to try it as an exhaustive search. You'd like to have a tool that can tell you something. So if we can determine an optimal weighting, we can both do the projection and we can do some analysis. Okay. Remington wants to know what you do if you have more than 2 classes. So just to answer Remington's question, because Remington is special and we definitely want to do everything that Remington wants, make sure we answer all of his questions. If you have more than 2 classes, we expand this thought into something called multiple discriminant analysis. You can think of this as Fischer on steroids. Okay. Instead of just having 2 classes where you're getting the covariance matrix, we're going to add a whole bunch of them. Add 1 for every class, add k of them. Okay. We're going to have more than 2 means, we're going to have k means. And we're going to take our between matrix and do it by looking at a priori probabilities, how many data points we have for every one, and then adding up all those different between matrices. So we can do between class 1 and class 2, We can do between class 2 and class 3, between class 1 and class 3. There's lots of different combinations we can add up. And so we take a total mean. What's our total mean across all classes? And we're then going to subtract each individual mean from the total mean from each individual mean. That way we don't need to worry about 1, 2, 1, 3, 2, 3, 2, 4. Instead, we'll just take a point in the middle. Come on. So we're going to take a point in the middle versus we have class 1, class 2, class 3, class 4, class 5. Instead of comparing the distance between these means, the distance between these means, distance between these means, instead we're going to take the distance between the middle and each of the individuals. And that's what this is. How many points do we have for each one? And just take those individually. So we're going to replace this concept with something very similar for our S between, our scatter between. Instead of just adding 2 of them, actually, we're going to take these scatters, individual scatters, across all the classes, not just across 2 classes, and add them all up. We still wind up with an SW, we still wind up with an SB. Or Sam and Joe, if you like them better. We're going to go back to that solution we had before. But if we had just 2 classes, there was a shortcut to get it. We're still going to go with calculating eigenvectors of the inverse of the within scatter multiplied by the between scatter. It's an 8 by 8 times an 8 by 8, which is an 8 by 8. And how many eigenvalues are there in an 8 by 8 matrix? Okay, let's go back. If you have a 2 by 2, how many eigenvalues are there for that? 2. They're the diagonal once you've made it diagonal into a diagonal matrix. So if you multiply this by what W transpose W, that will then form a diagonal. Once you are able to diagonalize it, then the diagonal elements are your eigenvalues. So for an 8 by 8, how many eigenvalues are there? 8. And some of them will be bigger than others. Right? Because we're taking matrices SB and SW that are positive semi-definite, they're symmetric. Because they're symmetric, that's because SB and SW are symmetric, they're going to be symmetric because our cross terms are going to be the same. Covariance sigma 1 and sigma 1, 2, sigma 2, 1 are the same. Because it's symmetric, the matrix is going to be positive semi-definite, and so your eigenvalues are not going to be negative. And I think they're actually positive definite, which means it won't even be 0. So we're going to get 8 eigenvalues, which are all positive. Some are bigger than others. So we're going to take the ones that are biggest, strongest, and take the eigenvectors that correspond to them. We have 8 eigenvalues. How many eigenvectors are there? 8. And so of those 8 eigenvectors, MATLAB, for instance, will return you a matrix. And every column in that matrix it returns is an eigenvector. And it will also return your lambda. Which is a diagonal matrix. And usually the programs will sort them biggest to smallest. So your first column of your W eigenvector matrix returned by your program corresponds to your first eigenvalue. Second one corresponds to the second. Third one corresponds to the third, and so forth. The bigger ones are stronger. And so if we want to then say, instead of projecting it to one dimension, if I pick 3 eigenvectors, you can project it down to 3 dimensions, 8 down to 3. Remington?
That's where they get like the full analysis, like looking at all those combined.
Yep. Principal components, hoteling, eigenvectors, principal factor, all these different names are all the same thing. All this are the same thing, just different ways of looking at the exact same mathematics to accomplish similar goals.
On the slide that you showed us, all the different ones, is it just different takes on it, or what differentiates those from each other?
What you're using as your data and what you're going to do with the answer once you get your numbers. So with multiple discriminant analysis, we can project it down to a different number of dimensions, and we can make it work for a different number of classes. We don't always have to project down to one dimension. If you've got 100 different features and you want 20 of them, pick the first 20 out of that really 100 by 100 big matrix. Your computer's going to cry when you ask it to calculate the eigenvector matrix for 100 by 100. But the idea is there. And then you're going to have several different weight vectors, depending on how many dimensions you're projecting to. Project to the first dimension by taking your raw data and multiplying it by your first vector. Take your raw data, multiply by your second vector, and you're projecting the second dimension. And so y1 versus y2 would be the lower projection, two-dimensional projection. Okay, so here's some examples with numbers. We have a point x1 and a point x2. Everything is 2 dimensions. So we've got 5 class 1 points and 5 class 2 points. So if we look at this, here's one data point, which is 3 and 0.2, 0.29 right there. That's a point right there. This guy right here is minus 0.1 and point whatever. So that's going to be that point there. So we've got 5 points, 1, 2, 3, 4, 5. Each one has 2 dimensions, 5 for class 1, 5 for class 2. And if we take these points and plug them in, we're going to get an optimal projection vector of 0.58 and negative 0.02, which kind of tells you what your slope is here. 0.58 that way, 0.2 this way with a negative slope. And if we think about projecting things onto them,
The green line always goes to the origin, or
yes. And that makes them nice and separable on that line in one dimension. So we can pick it as the threshold, project, and compare to a threshold. Here's some more points. 5 for x1, 5 for x2, everything in 2 dimensions. Now our optimal projection line takes us here. Again, project everything onto there. These are not separable, not linearly separable because of that naughty O right there. But this line here is still a very good line on which to project things, because dividing things there gets you the best results you can expect to get. Not perfect, not 0 error, but less error than other projections. If you projected this way, you would then have 2 errors. And here, because this has a slope which is approximately 1, you can see that both features have a weighting to them, both value. Whereas here, you could see feature 1 was a little bit stronger, it had more to it, because it's bigger, much bigger than this. Okay. Trying to tie this into stuff you have seen in other courses. I've said seen, not remembered, not learned, but seen. In signals and systems. I just finished teaching this for this. Miguel knows it really well. He's all ready for the exam number 2, where he's going to use this really, really well. There is a technique of evaluating your system, determining your transfer function of your system using eigenfunction methods. It's that whole eigenvalue, eigenvector, eigen is self. If you put a complex exponential into your system, if it's a linear time invariant system, you're going to get that same complex exponential out scaled by something. And what it is scaled by depends on what the frequency is. Frequency response. The idea is to put something in, get the same thing out, eigen. And we can use that to go and do analysis of our systems. students will do problems like this, you can calculate your transfer function. From image processing, the hoteling transform was on that long list of stuff. Here, our data points, our feature points, are the X and Y coordinates of all the points in this image. It's a really bad rendition of an airplane. Use your imagination. If we take those X and Y coordinates and calculate the eigenvalues and eigenvectors for them, it's going to return, I don't know if you can see it on the screen there, it's going to return an eigenvector there, and an eigenvector there. And if I had drawn the axes to be equal scale, they would have looked perpendicular to each other. And then there's going to be an eigenvalue determining this length and an eigenvalue determining this length. Whichever one is bigger is the dominant one. That produces an ellipse, which tells you the general shape. What is the general shape of this object? Without the details, but it tells you the general shape. Again, this is just showing you the same math, same concepts in other contexts. This is not what you're doing in this class, but the point is that the concepts are the same. There are draw. Here's another image with the principal and secondary axes, tells you the general shape. Some more points with some more general shapes. Same math, hoteling transform, different name, same math, different application, different data. Same idea. Where are your pixel points? Form things, find a matrix, find eigenvalues and eigenvectors. If you take linear systems here at any other university, it's offered in just about every electrical engineering department around the world. You can have a differential equation. Take a second order differential equation as the example here. You can write it, excuse me, as two first order differential equations, which can then be written in matrix form. If we want to then diagonalize that matrix A, if we want to diagonalize this matrix A, we can calculate the eigenvalues and eigenvectors of it. That's going to create V, it's used V in the math there, but it's the same thing as the W we just did. We multiply pre and post by W transpose, produces some new vectors, which are now diagonal. And the solution to this differential equation is going to be e to the -1 and e to the -2t with some coefficients out in front of it. Which, if you think back to your introductory differential equations, you did a characteristic equation, you solved that polynomial, you found roots. Sound vaguely familiar? And those are the same things here. But when you get into the 600 level class, we don't do it with the linear method. We put things into matrices because there's other things we can do once we get it in the matrix. And we like to diagonalize it because then there's other stuff that follows on for the solution for other analysis and other big grandiose things you can do. But it's all built about taking a matrix, finding eigenvalues, finding eigenvectors, -1 and -2 are the eigenvalues corresponding to that matrix A. And you're going to take this matrix of eigenvectors, and you're going to pre and post multiply your equation by it, which diagonalizes it, which allows you to solve and analyze and do other really wonderful things. That's just the beginning part of this course. Again, the idea is for you to see the same math shows up. So going back to our situation, trying to find ways where you can process things and find a better projection. In the past, I've had students ask, why can't we just choose the difference of the means? So here's an example with blue O's and red X's, 5 points of each. The optimal projection is just to take feature 1. If we just took the two means and took the two means of the vector, you're going to get this diagonal vector. And that projection is not optimal because there's a lot of overlap that results from it. So that's why you need to take the difference of the means and scale them by the inverse of your within scatter matrix. Just the difference of the means alone is not adequate. Okay, A through Z. You guys are getting very comfortable with this data, very used to it, right? You love it. It's your best friend. You can't wait to do more of it. So here it's taking that and projecting onto 2 dimensions. Now remember, you did the homework 2 with the scatter plots, and you were looking at breaking into 2. Did you ever get this good a separability? Probably not. You got some, but here X's and A's are very separated. Everything is pretty separated from each other. They're sometimes close, but everything there is separated. They don't intertwine. So I bet if you go back to your scatter and look at everything in 2 dimensions, you can never find any one pair of dimensions that would get everything where they are all separated. You can separate X's from A's with this combination, but if that combination would not separate your S's and Z's. And yet by projecting on the best 2, which are linear combinations of the 8, so it's not just taking 2, it's taking combinations of the 8, bringing it down to 2, you can get separability. Here's the test data. And these are using the same projection vectors calculated for train. M's behave nicely. X's and A's are a little bit separated, but we got one M scattered over here with the N's, affinity to the N's. And we've got the Z's and S's are kind of jumbled in together. X's and E's behave pretty well. It's a kind of matching the results that you saw when you did project 1, which things were mixing, and the fact that test 1 didn't really separate very well. Here's test 2, eval 2 projected onto the best 2 train dimensions. Here, things are a lot better separated. I think the M's are off the screen. Because eval 2 is a lot more similar to eval, or yeah. That's again without the M's. Train without the M's, you now can see much better how well things are separated. Without the M's, they're a little bit mixed. And if we calculate the best projection without the M's, it can separate them even further. So those M's are such an outlier, they have an influence, which you don't really need. So we can get things much better separated if we just leave those M's out. Okay. Thoughts? Raise your hand if the big picture is clear. What is the big picture? You can reduce your feature dimensions. What else is part of the big picture?
Reducing your feature dimensions since the new features are determined by the old one.
The number that you're actually calculating with is going to be smaller. So while you're using all of them, but we're bringing it down to the number that we're actually going to do calculations with. So think of nearest neighbors. When you calculated a distance, how many differences in squareds did you do in nearest neighbors when you calculated every distance? 8. And then you had to do a comparison of 1 point to 100 training points. And so that was 8 for each one of them. If I bring it down in dimensions by projecting, we now have 2. That makes a difference. Now you need to project, but these 100 you project once. And then each one individually you project once. And then you've got fewer distance calculations. So that can make a difference. Now, again, you're not working with big data sets in here. It's big enough you can't just look at them. But they're not really what we consider big data sets for the real world. But it can reduce your computations, even if you're using all the information. And you can use it to analyze which features are stronger, to make some other decisions. So if you're doing a master's or doctoral thesis and you need to say, why am I doing this? Which features should I use? You can evaluate them and say, well, these ones here, these are stronger because mathematically they play a bigger role in separating the classes. Rather than, well, I randomly picked mu02 and mu30 because they kind of look nice. You can say mathematically why you chose them and back it up with facts. Okay, I'll see everybody on Thursday.